Live in 3, 2, 1. Okay, there we go. We got it. We're up on YouTube now. So welcome, everybody. This is the first official, I suppose, technical episode of the Bitcoin Cash Coffeehouse. And yeah, it's a new series focused on solving problems, I guess, through discussion on Bitcoin Cash. And it's more of a technical topics. I know my own show. I am a little more casual, but I like bringing experts because I'm not technical by any means. But today we were talking about the difficulty adjustment algorithm on Bitcoin Cash. And before we get into the topic, we'll have our guests introduce themselves. So we'll start with Tom.
Hi, I'm Tom Harding. I've been working in Bitcoin development since 2014. In late 2014, Mike Hearn and I started Bitcoin XT because we had both had features rejected from Bitcoin Core that we felt were important for P2P scaling. I found myself working on difficulty quite a bit. I proposed the WT144 algorithm for the Bitcoin Cash fork in November 2017, but that wasn't chosen. One of the reasons that we're here today. And then after that, I've also been working on improving that, the WTMA algorithm and lately the RTT algorithm that I'm testing out on another chain.
Cool, thank you. Scott?
Okay, I'm Scott Roberts. I'm known on the internet as Zowie, Z-A-W-Y. And I'm known for working on difficulty algorithms all the time, helping a lot of altcoins with their algorithms. Most of them using LWMA. This year I've been working on consensus mechanisms and trying to find a way for altcoins to have the same kind of security as Bitcoin.
Awesome. Jacob?
Hey, yeah, so I'm Jacob Elisosoff. I'm in New York City. I run a small crypto investment fund. So I'm not a full-time developer on this stuff the way some of the other guys on this call are, but I did take an interest in DAA and specifically in the EMA type exponential smoothing, exponential moving average parts of it, just partly because it seemed like may not be the most important part of the whole system, but it's a part that, you know, that Bitcoin, that BTC clearly is suboptimal at, and where there's some interesting math involved. So I played around with it. And I'm mainly here working from my memory banks. I'm not up on all the latest developments, but I'll chip in what I can.
Cool. And Jonathan?
Hi, my name is Jonathan Toomim. I'm a miner and a developer. I first got involved in development around 2015 with Bitcoin XT. I made a few minor contributions to Bitcoin XT. And then also helped co-found the Bitcoin Classic project the next spring with Gavin and a few others. I've gotten interested in the difficulty adjustment algorithms recently because, as I've seen, the performance has gotten worse. We've had some oscillations that have always been present, but have gotten much higher in amplitude. And that's, I think, starting to impact the user experience. So I thought that it's about time to get people organized and get a solution to that deployed.
Cool.
So yeah, in like March, I posted a video about the oscillation problem that we have currently and how EMA, specifically Jake's code, can fix that.
Gotcha. Yeah. So yeah, I'll give an overview of the general problem. If you're new to this, we are gonna get technical, but I'll do the normie explanation quick. And so when Bitcoin Cash forked from BTC, we had to change the difficulty from changing every 2 weeks, how hard it is to mine. We had to change from every 2 weeks to basically every block. And the first one, I guess the first one wasn't. It was called the emergency difficulty algorithm. And when a bunch of blocks didn't come after a while, the difficulty dropped really low, and then there were a bunch of turbo blocks really fast, like every 20 seconds or something ridiculous when it should only be 10 seconds. And then I believe in November that was forked, and now we have the current DAA. And so yeah, that was in November. So this is Jonathan sharing his screen, and then we got the new difficulty adjustment algorithm, and there's basically oscillations, and so miners will game it. So they'll basically mine it really fast, difficulty goes up, and they'll all just stop mining it, and we'll have no blocks for a long time. And this is not good for the user experience, because part of the user experience is waiting for confirmation sometimes, even though Bitcoin Cash is heavily relying on zero-conf. Zero-conf only works when you expect a block in 10 minutes. So yeah, that's really the problem of it now. And here, Jonathan is showing these oscillations with the purple, I believe. You want to kind of explain this chart?
So I'll give a quick overview. So this left section, this is all the Bitcoin BTC history. So this is what the 2-week adjustment looks like. You've got in red, I'm not sure if it shows up very well because it is high resolution, but this little red line is the difficulty, and it adjusts every 2 weeks. And the purple is the hash rate, estimated hash rate. And there's some noise, but it's basically white noise during the BTC era. Once we forked and had the EDA, we saw these periods, long periods of very low hash rate, with occasional bursts of extremely high hash rate. And that's because the difficulty algorithm was not keeping profitability parity between BTC. So all of Bitcoin's miners were joining BCH for a short period of time, mining
sorry,
a
1 second.
gazillion blocks.
Scott, could you turn your speakers down a little bit? Scott, could you turn your speakers down a little bit? We're getting an echo. Scott?
Okay.
All right, go ahead.
Yeah, so we got these bursts of very high hash rate that lasted for 2016 blocks, followed by bursts of very low hash rate that lasted until the EDA kicked in and dropped the difficulty, at which point the cycle would repeat. So that was the EDA period, and that's the left half of the screen. That's like this section here. Then in the next section, we forked in the DAA, which is Omri's algorithm, and that made the hash rate much closer to constant, but we still had these spikes. We still had an oscillation. Instead of being a 2016 block oscillation, though, this was a 144 block oscillation. And so we'd see hash rate go high and then low for 130 blocks, then hash rate high again for a couple dozen blocks, and more or less repeating. And that oscillation happened immediately. That started happening in November. November 13th was when the algorithm changed, and we saw it November 16th. But recently, it got a lot worse. Like in January, we saw the oscillations be like 20 exahashes in amplitude. So the difficulty, or the hash rate was normally about 3 exahashes, and then it would jump up to 20 something exahashes for a dozen blocks, and then back down to 2-3 exahashes. So that was a much worse example, but of the same problem. It's still the same source. The only thing that changed is miner behavior.
Gotcha. Yeah, so maybe they found their own algorithm within their mining pool or whatever to kind of maximize profitability.
I think actually what happened was the amount of hash rate that was actively switching chains increased. I think there is one large pool. I think I know which pool, but one large pool I think implemented the code to switch their hash rate between Bitcoin and Bitcoin Cash based on profitability. And I think that pool had about 15 to 20 exahashes of hash rate. And like there are rumors, there are allegations of who it is. I just haven't found like convincing proof that it is actually this pool yet. So I'm not naming them out of hand, but yeah, it's probably just one entity changing their pattern. Like we knew that BTC.top was doing this as far back, well, at least as far back as January 2018. They might have been doing it since November of 2017. We don't really know. But the worsening of the problem in October of 2019, and then again in January, that seems to just be because more hash rate switched to this greedy strategy.
Gotcha. Gotcha. Does anybody else want to comment on the current DAA and the problem?
Well, actually, can I just jump in with a couple of comments on what Jonathan was just saying? I mean, you guys are actually interested to hear feedback on this, but my understanding is that the main goals, like the miners aren't really the problem, right? The problem is the incentive. So my understanding is that the main goals of the difficulty adjustment algorithm are, first of all, most basically, you're trying to keep your blocks every 10 minutes, give or take. If your blocks all start taking an hour, that's a problem. This is just a very obvious user problem. You can't be waiting 10 minutes for a block. But on the other hand, we also want to incentivize miners to keep those block times reasonably consistent, right? We want to avoid the situation where miners make the most money if they do these crazy oscillations of 100 blocks in an hour and then no blocks for hours. Are those the two main goals? To keep the blocks around 10 minutes and to prevent oscillations?
So I think that there's some nuance that's needed on the 10-minute thing. Like, we don't want to target exactly 10 minutes. That seems like a really good idea at first, but if, for example, we had a deterministic algorithm that made all blocks between 9 minutes 30 seconds and 10 minutes 30 seconds on the dot, no blocks less than 9 minutes 30 seconds, that would actually be really bad for Bitcoin Cash, because that would cause very high orphan rates. That would cause a lot of competing miners to find two blocks at nearly the same time in less time than it takes for a block to propagate between the two, and to get people fighting about which block was going to be the correct next block. And that increases orphan rates, which in turn reduces the safe transaction capacity that we have for transaction throughput. So we do actually want to have the blocks be spread out over a fairly large interval. But yeah, on average, it should be 10 minutes.
So we want something like a Poisson process or whatever, like one of the, stochastic, but with, they shouldn't be getting longer and longer or shorter and shorter over time, right? We want them to sort of have some rough consistent average.
Right, and one thing that we can describe is we don't want the block interval of adjacent blocks to be correlated. Like, we don't want block 600,000 to have a very similar interval to block 600,001. Like, if 600,000 is 2 minutes and 600,001 is 1 minute, that's a problem, because we're concentrating all of our high frequency blocks in one cluster. And that means that some other time interval, we're going to have 1 hour blocks. So that's really how the burstiness of the hash rate causes problems. It causes long intervals of slow block issuance, which results in long confirmation times. And we actually see that in this graph. This is the confirmation time graph. So ideally, blocks would take 10 minutes on average.
I think you got to share it here.
Oh yeah, sorry, I forgot about that. Let's do that. So yeah, here's the confirmation time graph. This is all time. So you can see there's a little bit of wonkiness going on in 2009 because every now and then Satoshi would shut off his computer and hash rate would go off. But like post 2011, the confirmation time was very close to 10 minutes on average. When there was a price crash and people would shut off miners, it would increase to maybe 12 minutes on average. And when the price went up and a bunch of new miners came on, the confirmation time would decrease to about 8 minutes. But overall, it's very close. Then as soon as we got the Bitcoin Cash fork and we got the EDA, we had these really long periods in which blocks were being mined very infrequently. Sometimes it would take 4 hours between blocks. And for many days or weeks, we had 40 minutes. So if you pick a random block interval, it's more likely to be a long block interval than a short block interval. And that was causing huge problems during the EDA period. Once we forked in the DAA in November, you can see immediately that performance increased dramatically. But it didn't quite go down to 10 minutes, at least not consistently. Sometimes it was a bit above that. So let's see, the bottom of this window, of this Zoom window, is actually 10 minutes. And so it was usually a little bit above 10 minutes. And then, it got a bunch worse. And so the confirmation time is how this directly impacts users. We don't want bursty hash rate because that means that the average confirmation time is going to be longer because the average transaction is going to happen during a longer block interval. So that's like one aspect of the problem. And again, like you were saying, the issue isn't that miners are being malicious. They're just following their incentives. And as a developer community, we made the mistake of using a difficulty adjustment algorithm that encouraged rational miners to mine by switching chains based on which one's more profitable. And we need to use a difficulty adjustment algorithm that keeps the hash rate switching to a minimum and keeps the profitability between chains as close as possible to equilibrium at all times.
Sounds great. Does anybody else have any comments about the current DAA? Oh, Tom, you're muted.
It struck me when John showed the oscillation chart how exactly similar it looked to the prediction of what was going to happen for that algorithm that was generated by this very same simulator, simulator back in 2017. I shared it in the chat.
Okay. Yeah, I have that open. Here's my UI for that simulator, and here's those oscillations in difficulty. So this is again like the same thing this is simulator results. This is the 2017 simulator just with a new UI, and we again see that spiking. And this is just what happens when miners are following their rational interests. So yeah.
So yeah, that was a simulation of what was predicted to happen, and then it did happen.
Right.
Gotcha. So yeah, this was the file.
The same exact simulation. That code existed 2 years ago and was run. That same chart.
Right. Yeah. This is the 2017 simulation, and this is the actual data. So like, if we get the scale right, let me change this. Yeah, if you get the scales right, the actual data looks very similar to the simulation data. And that was just what Tom was saying.
The way that simulator works, that it simulates what real world miners would do, like John said. And because I know that back in that time period, there were other simulations being done on the ABC side that focused like a lot on sort of faithfully imitating the way mining works by doing a lot of by actually doing hashing. And this didn't have any modeling of miner behavior at all. So going forward to evaluate algorithms against each other, I mean, I don't know if anyone disagrees, but this framework is the framework that's already proven itself, and any new algo should be plugged into here to allow it.
Yeah, the critical thing is comparing a multi-coin ecosystem or comparing the algorithm performance in a multi-coin ecosystem, because it's really easy to make a algorithm that will adjust the difficulty based on the hash rate if there's only miners choosing whether to mine or not based on if their electricity price is less than what they're earning. That's a very simple scenario. But once you start having multiple coins going on and people having the choice about which coin to mine, then you get a much more complex system. You get much higher chance for oscillations and for shenanigans.
Yeah, especially when you have a minority coin, playing in the sandbox of the SHA-256 hash rate, which is so enormous. Even actually almost, I might even say all of the difficulty algorithms in that simulation, including the ones we've been talking about, don't really hold up very well in the face of a giant hash rate attack. I think I figured out once that if 50% of the hash rate decided to attack BCH, and then left, they could probably make the next 10 blocks take a week or something like that. So it's a really big problem that, for other, reasons, because of friendly hash rate and things like that Bitcoin Cash luckily hasn't experienced yet.
Yeah, I'm less concerned about the huge hash rate short-term attack, because those attacks are inherently very expensive. especially if you can increase the difficulty within the first 5 blocks by like 5% and make it so that those blocks are only 95% as profitable as mining BTC, then like there's a strong disincentive to do that. And the only incentive to do that kind of attack is griefing. If BTC miners really hated BCH the way that BTC maximalists do, then they might want to destroy BCH, and they could do that by, or they could try to do that by increasing the difficulty a bunch.
It's actually amazing how miners have shown a complete disinclination to attack each other. Even the BCH BSV split, where everybody was threatening to attack each other, no one actually attacked each other.
That's not entirely true, but never mind. I can't say anything more about that. So I think one of the reasons for that is because we think of miners in terms of BTC miners or BCH miners or BSV miners, but in reality, what they are is SHA-256 miners. And their profitability is determined by the profitability of the whole SHA-256 coin pool, not by any one coin.
Right.
BTC miners benefit from BCH's existence as long as they're mining BTC, because BCH will reduce the difficulty for mining BTC in proportion to the profitability of mining BCH. So as soon as like the halving happened for BCH, that was like what, a month earlier than BTC's. As soon as BCH's halving happened, the profitability of mining BTC dropped by a few %. And then as soon as the halving happened for BTC, the BCH profitability dropped by about 48%. So all miners are in this together, and the incentive to destroy another SHA-256 chain isn't there. The incentive to protect other SHA-256 chains generally is. So I think that's one of the reasons why we don't see the kinds of miner shenanigans as often as you might expect.
Yeah, agreed.
Of course, there are still 51% attacks. Small coins do often get 51% attacked, like Bitcoin and Gold did. There's like half a dozen major events like that. So we do have to be concerned about that kind of attack. But the 51% attack isn't a mining attack so much as it is an exchange double spending attack. And that's where the profitability comes, not from the mining itself.
Yeah. Well, no, like what you said earlier, it would come from malice. It wouldn't come from incentive if it ever happened. But there's actually even easier attacks that if you really just wanted to cause problems, it's not even, you don't even, the timestamp issue is, I hope maybe someone will talk about it a little bit, because that's a vulnerability in all the current chains.
Cool.
Negative timestamps and minimal timestamps, basically timestamp shenanigans.
Yeah, there are a few different things that you can do with timestamps. So currently, Bitcoin as well as Bitcoin Cash have a couple of rules on what timestamps can be. The timestamp cannot be earlier than the median timestamp of the last 11 blocks. So basically, like in practice, this means if you take the block 6 blocks ago, the next block's timestamp can't be less than that block's timestamp. So you can have a little bit of future past manipulation, but that usually bounds it fairly heavily. Then the second rule is that if a block has a timestamp 2 hours in the future, then it will be marked as invalid upon receipt by most nodes. And so that gives you a maybe 3 or 4 hour window of timestamp manipulation under normal circumstances on Bitcoin or Bitcoin Cash. But there are some things that you can do to make that abnormal. You can still do some really weird timestamp stuff. For example, if you fork off of the Genesis block, or you fork off of a block a few months ago, then you can go up to 2 hours ahead of now, and then all the way back down to 6 months ago in the span of a few blocks. And that allows you to do some strange things with the difficulty.
What's that called again? There's a word for that.
I didn't know there was a word for that, but
It's the long something attack. I can't remember. Maybe I'm misremembering. I think, anyway.
But yeah, with some algorithms, for example, if you did that kind of attack, if you started several months in the past and manipulated the timestamps very widely, you can mine an infinite number of blocks in a few seconds. This is especially true of difficulty adjustment algorithms that use the median of 3 or median of X for determining what the timestamp is or what the chain work is. As you can mine like 2 blocks way in the future, then 1 in the past, and then another block in the future, then another 1 in the past, and you can keep going back and forth between those. And if you do it right, you can keep the median time passed of the last 11 blocks low, but the median time of the 3 blocks high, and you can do some other stuff. These are theoretical attacks that aren't usually practiced, but it's important to make sure that when we're designing difficulty adjustment algorithms that they don't suffer from these kinds of attacks.
But yeah, so as you say, I mean, I think just like in practice, there's all these potential timestamp shenanigans, but in practice, they haven't been a huge problem as I understand it. So I think most of the work, that the community and the people on the call have done on the difficulty adjustment algorithm has been in the more theoretical context of, let's suppose there are no timestamp shenanigans. Let's suppose all the block times are accurate, more or less. And then given that easier world to work in, how can we get rid of these oscillations? How can we adjust the algorithm, right? Is that fair to say that the timestamp shenanigans have not been the major problem that people have worked on here?
I've always kept the timestamp attacks in mind. I consider that an algorithm that has an obvious manipulable aspect with timestamps is like having that is a deal breaker, but it's not the primary optimization target. We don't want the algorithm that is maximally unmanipulable because we know what that algorithm is and it's epically bad. If we just hard code a constant difficulty, that means that timestamp manipulation attacks will never be a problem, but it's completely useless. So we do want to make sure that, like, first and foremost, we have block intervals, like real-time wall time clock measured block intervals that are reasonable and well distributed. And secondly, we also want to make sure that there's no incentive to do something wildly malicious with the timestamps.
There aren't any timestamp attacks that are possible if each block if the timestamps in blocks are sequential. Monotonicity, I think people call it. That's the first rule. And this is a requirement that's actually part of any distributed consensus. I look back to Lamport's 1978 paper on clocks ordering, and it's actually a requirement that, and so it's kind of like they didn't realize when BTC came along, and the medium of time passed was sort of like a patch, and that you get your security most of it from that, and by relying on that instead of each block being sequential. And that's the first rule. The second rule is to not make such a future timestamp limit 2 hours in the future. It only needs to be significantly longer than 2 times your propagation delay of blocks, and it should also be significantly less than your average block time. And that's so that the nodes and everybody are forcing a short, reasonable range of timestamps on the miners, so that the voting population, the number of hashes in each block, can be approximately counted and then averaged, over. To get a better measure, you have to wait several blocks because it's random. Anyway, just wanted to say you can prevent timestamp attacks.
You can certainly easily code the prevention of non-monotonic timestamps. The reason, I think it's important to remember why Satoshi did it the way he did, though. The reason he allowed future timestamps and significant and negative timestamps was to try to make the blockchain time able to be effortlessly track real time without any. There's no incentive either way for people not to follow current time. So I think that's the word. I'm not saying that. I mean, in RTT, I definitely banned any future timestamps and any negative timestamps. But RTT contains incentives for the miners. It has an incentive. If you want to mine a 1 second block over the past block, it's 80 million times more expensive. But any non-art real-time algorithm doesn't have that. So it would. I haven't done the experiments, but it would be more likely, I think, for the natural clock either to drift all the way and just stay at the future time limit, or to stay at the minimum time limit in the past, whatever you have it set as. It may not be a big deal, but that's why Satoshi did it that way.
Yeah, I don't think there is an incentive to have the clock drift. I think, so Satoshi made it so that there was no enforcement of timestamps because it's hard for people to agree on what the true clock time is. It's hard to build a consensus mechanism that allows people, that provides an incentive for people to agree on the clock time. And B, if he prevented any rules from applying based on clock time, that just made it so he didn't have to try to solve that problem. It was like a reduction of complexity issue, I think, for him.
Well, if you bring in the future time limit to very tight, miners are going to reduce time limits so they don't hit that limit. That's why it's 2 hours out, so that nobody will have to worry about hitting it.
Right. Not having to worry about it is a really good thing when you're writing version 0.1 alpha of any given code project. But we do have systems.
The developer having to worry. I'm talking about miners having to worry. With that algorithm, the miners don't have to worry about hitting the future time limit at all. And with blocks so fast, I'm sure it can be brought in. It's just that's why he did it that way.
Yeah.
Well, I mean, I think we're agreeing with each other.
I mean, if you had a future time limit of say 30 seconds, why would the miners not able to keep this clock that accurate?
So
I mean, why is that a problem?
Stratum jobs often last for more than 30 seconds. So the mining ecosystem works with a pool usually that's running their Bitcoin node, Bitcoin D or whatever. And that creates a block template, which it then passes over to the pool software. And the pool software converts that block template into a Stratum job, which it then sends off to the mining hardware itself. And the Stratum protocol allows for the timestamps in the blocks that are being mined to be incremented, but not decremented. And it allows for very wide changes in how much you increment the timestamps, and it provides basically no restrictions on that. And the mining hardware ecosystem is not that flexible, not that easily adjusted, because Bitmain, InnoSilicon, all the major mining manufacturers have legacy hardware that's 3 years old, 4 years old, that's still in active use. They've got maybe a dozen models of machines. They don't want to have to patch their hardware just to support one change in a coin that represents 3% of the total SHA-256 hash rate. So ultimately, we are constrained by the amount of resolution that we can get out of Stratum. If Stratum allowed for mining hardware to decrement the timestamp, then we would not be able to create a rule that forbidded blocks from being in the past. Because that would basically be a rule that could brick a lot of mining hardware. It could brick hundreds of millions of dollars worth of mining hardware that had been deployed, and it would be a violation of the social contract. If we set a rule that prohibits timestamps from being more than 30, 50, 120 seconds in the future, that could brick some mining hardware. And the amount of mining hardware that would be bricked by that would probably be dependent upon how far in the future it was actually done. yeah, I guess we want to try to make sure that we have something that's compatible with mining. But we also want to make sure that we have rules that are compatible with the small amount of clock skew or real-time clock drift that we see in actual systems. And what we've seen with Bitcoin blocks is that blocks do happen in the past. We do sometimes see that the timestamps of the following block will be earlier than the previous block. And obviously, later blocks came later. Blocks at a higher height must have been mined after the previous block. But sometimes we see the timestamps be earlier. And that's just probably almost certainly because not everybody runs an NTP daemon client on their servers. Not everybody is careful when they're running a pool about making sure that their computer's clock time is accurate. Yeah, that's I think the only reason why we've seen negative timestamp blocks in the past. There is another concern for getting rid of the negative timestamp intervals, and that's if somebody does decide to set a block really far in the future. Let's say somebody sets a block 2 hours in the future, and they have 10% of the hash rate. And they do this every time they can. That means that on average, that one person is going to be moving the timestamp forward by 120 minutes per block for 10% of the blocks, or 12 minutes per block on average. And that can like drift the clock until you hit that limit. So some people are concerned that somebody might do that in order to get the difficulty a little bit lower or something like that. And that we should allow negative timestamps in order to reset it back to real time.
Just to be very clear here, when we say negative timestamps, we mean timestamps that are before the previous block, right?
Not negative timestamp intervals,
right.
Like negative block intervals is the correct way of phrasing it.
I have a question for Jacob. What you had invented in January 2018, the simplest difficulty algorithm ever, which Scott Roberts later fell in love with, and it is very interesting. But I'm curious about your you called it simple exponential, and it's also the ACERT algorithm that Mark Lindenberg had published and done a bunch of thought about. But you at the time you just said, "Oh, it has these amazing properties." I mean, do you see any problems with that algorithm? Or you two, I'd like to hear talk about it because I know you thought about it a lot.
Could you first describe what the simple exponential is?
I'm going to try. I'm rusty, so people will probably have to correct me. But let me give my explanation will be a little less technical because I'm a little far away from the technical piece.
I'll type it in chat.
Okay, but so just to give a short spiel on the idea. I mean, my understanding of the idea here, and I think this applies really to most of these exponential decay related algorithms like WTEMA and all these other ones. They're in a sort of category of family of algorithms. So the way I think about it is, you have this general problem. You have these blocks that have some times, and the block times in the past, maybe you look at the last day and all the block times are 12 minutes, 20 minutes, and you look at that and you say, okay, the block times are too long. We need to make the block times shorter. And so to make the block times shorter, we're going to reduce the difficulty. We're going to make it easier to generate a block. Or maybe you look at the past day and all the block times are like 1 minute, 2 minutes, and you say, okay, our difficulty is way too low because they're finding blocks much too easily. So this is like a qualitative description of the problem. You have these block times. How are we going to adjust the difficulty to correct that, to push in the other direction? And we don't have to push it all the way. We just have to improve it. And so the simple thing that I think maybe the original emergency difficulty algorithm or something did is you say basically what I just said. You say, okay, we're going to look at the history of recent blocks, and we're going to see if the average block time is more than 10 minutes or less than 2 minutes, and we're going to tweak the difficulty accordingly. But the very crude sort of intuitive way to do this is to do something like, say, take all the blocks from the last 24 hours look at the average time during that period, and then see whether we need to move the difficulty up or down. And as soon as you have a crude window like that, you enter a world of pain, because you get things like, okay, well, maybe there was a really long block that was 23 hours and 55 minutes ago. And then all of it, so then for a while, it looks like the average block time over the last day is way too high. And then that one weird block moves over your 24-hour threshold, all of a sudden is dropped out of your averaging window. And now maybe your average goes all the other way, because all the other blocks, it turns out, are less than 10 minutes. So having a very fixed window like 24 hours and only looking at the average within that window is mathematically inelegant, and it leads to, I think it's kind of fundamentally leads to these oscillation problems if you step back a bit and look at how the oscillations are coming in. So the basic intuition to me of all this exponential stuff is, instead of saying we're going to take a fixed window like 24 hours and look at the average block time during that period, we take a more gradual smoothing of the weighting, and we say the most immediate block gets a high weight. The block a little bit before that gets a slightly lower weight. A block a day ago gets a somewhat lower weight. A block 2 days ago gets a significantly lower weight. And there's sort of a very traditional way to do this for moving averages, which is to have this exponential decay. So that is, like, to me, the big picture of what all these algorithms are about, is saying that we're going to take the average, we're going to figure out the difficulty adjustment we need based on the average block time of recent blocks. But when we calculate that average, we're going to do it using this smoothly decaying, exponentially decaying weighting, rather than a fixed window. That makes sense?
Yeah, but I was asking about ACERT, or simple exponential, where you just reset. The thing about that one is you completely reset from the genesis, or from the activation block.
Can I give it a go?
Sure.
Yeah, so one of the really cool things about the exponential moving average family of algorithms is that there's a lot of different ways of writing them. And this is something that we often see in math when you're dealing with exponentials. You see a lot of really strange formulas that can be interconverted that you wouldn't expect, like, the famous e to the negative I pi equals 1 formula, Euler's formula. It's really strange that you can relate pi negative imaginary numbers and get something that's 1 with the exponential function, but you can't. And we also see a lot of those strange, unexpected coincidences with the exponential moving average formulas. For example, like Jake described the EMA in terms of an exponentially decaying weight for each block. So if you want to calculate that using that formulation, you would have to sample every single block in the entire history of Bitcoin in order to make that calculation. And that sounds quantitatively impossible, basically. But it turns out there's another much easier way of calculating the same thing. And instead of doing an infinite series calculation, you can just do a simple recursive formula where you calculate some function based on the most recent block and then the one block prior to that. And so given those 2 blocks, given like 2 taps, you can perform exactly the same work as doing an infinite number of taps. And that's cool. And that's something that's fairly unique to the exponential moving average. But the thing that Mark Lunderberg figured out, or maybe Jake, I actually don't know who came up with this idea first, but you can go a step further. Not only can you do it in a recursive fashion, you can also do it in an absolute fashion, still using 2 blocks. So you can calculate what the current block's difficulty should be given the most recent parent block's timestamp, its height, and then the fork block or the genesis block's timestamp, height, and difficulty. And conceptually, the way this works is that you have like some target timestamp. You can say, okay, if block 1 happened at time t equals 1 second, and we want it to be 600 seconds per block, then the next block should be 601 seconds. The block after that should be 1201 second, et cetera. And so you can calculate what the timestamp should be for any given block. And if you get ahead of that schedule, then you can say, okay, we're a little bit ahead of schedule. That means we should be at a higher difficulty. And you can say arbitrarily, let's say that every day in advance of the schedule we get, we double the difficulty. So that way, if we're 2 days ahead of schedule, we quadruple the difficulty compared to the fork block, et cetera. And that formula allows you to specify what the target difficulty should be based on only the fork block and the most recent block. Again, we're talking about doubling the difficulty for every day. So you end up with an exponential function there. And that exponential function ends up being the formula that Mark Lenneberg came up with in his assert paper. And it's also mathematically identical, coincidentally or whatever, mathematically identical to some versions of the recursive EMA formula. Not all of them.
If you make an assumption.
Yeah. There's basically like, so the WTAMA formula that Jake does works like this. If the most recent block interval was 0 seconds instead of 600 seconds, then we should decrease the difficulty for the next block by, let's say, 1%. If it's, increase block difficulty by 1%. If the block interval is 20 minutes instead of 10 minutes, then we should decrease the difficulty by 1%. So there's that like 1% plus or minus thing for a given timestamp jump in the future or in the past. The only difference between that formulation and assert, the only potential difference is in whether that's adding 1% and subtracting 1%, or if it's multiplying by 101% or dividing by 101%. And if you do the multiplication thing, then you're doing repeated multiplication. And when you convert that into a multi-step formula instead of a single-step formula, you end up getting an exponential out of it. But for simplicity, the WTAMA algorithm uses addition instead of multiplication. And so that gives the only difference, or the only deviation in the WTAMA algorithm from the assert formula.
Yeah, just to clarify a couple of things. I think the WTEMA, I think that's Tom's algorithm, right? That's so there's the very, because what I remember about that algorithm, and this actually gets back to your original question, Tom, is like, why wouldn't we use this extremely simple algorithm? And one of the reasons I think was that to calculate a crude exponential does involve floating point math, whereas WTEMA is like really I mean, this is to me was the sort of cutest innovation of it, is that it's calculated in a way.
You had already provided an integer version of it too.
What's that?
You had it provided 2 implementations of it.
Well, yeah, but the integer version is a hack. I mean, I wish it well, but whereas the WTEMA is actually elegantly done in integer math. So that there are some real. I poo-pooed this when it was first brought up, maybe by Scott. I can't remember, but I mean, it turns out that when you're doing floating point math, then yeah, you could get discrepancies across hardware and stuff. So it is probably a nice thing to avoid.
So Jonathan, I think the reason that you have a little bit of confusion on historical, because the like I went in your UI and the simple exponential doesn't show up there, and it's because you forked from the Neil's code like before Jacob added it. He added it in January 2018. So you really need to rebase that thing on the master.
Yeah, the Git history for the code base that I was working on did get messed up. I actually started working on it based on a zip file that Shema Chancellor handed to me. And it had some uncommitted changes, and I didn't know whose changes they were. I thought they were Shema's, but in retrospect, they were not.
Well, he's right though, that because I did the WTEMA, which was just I took WT144, and then Jacob had done the other work on the EMAs, which was clearly better as an average. It's just clearly better. So I just combined those 2 things, and of course, it's not even an invention. It's an exponential moving average is like one of the simplest things on the planet.
Yeah.
But it is. I don't know if I have another chance to mention this, but one of the things that's important with Karol's. I know you and Karol went back and forth on that algorithm, but one of the things he was doing was averaging, and also what LWMA does is it averages a bunch of block times, just the times, and LWMA does that. And Karol's thing had like that in the denominator, and then the hash or the average difficulty in the numerator or something. And what's really important to me, and I don't see how, maybe someone could tell me why this doesn't apply, but if you're taking a sample, a time sample, and you're trying to weight it into whatever algorithm you have, you're taking a measurement that was made while the miners were using a difficulty that you know what difficulty they were. So that time sample should only be applied. It should be weighted by the difficulty at which it was sampled. And that is the case with WTEMA. It's also the case with the simple exponential, aka ACER, because that one just redoes the entire calculation from the beginning every single time. So, but those two do that. But LWMA actually doesn't do that. LWMA also is just an average. And Scott and I have talked about it, and I think you could say something, Scott, but I think he said that it seems to work just as well or even better. I don't know how it could work better, but
okay, yeah, we talked a fair amount about this. Testing your WTEMA, applying the time to each difficulty, very, very reasonable. I understood, why you did it. And it sounds like you should keep the times with the difficulties that they apply to. But in testing, just breaking them apart worked out better. And what I have found out is that the reason is that you can't take a single difficulty and a single solve time and accurately measure the hash rate from that. It actually gives you a bad.
That's a separate issue, because you're still if you're going to look, you have to look at, as you know very well, as you look in the past, you have to, if you're going to get an estimate of the current hash rate, especially with the traditional algorithm, you can't just look at the most recent estimate of the hash rate, because it comes apart and diverges. If you just took the Bitcoin algorithm and took it from 2016 blocks down to one block and retargeted every single time, it completely blows up. And the reason is because you're estimating the hash rate from a highly variable sample. That's why they want 1,000 samples. But so you have to look at multiple, but it's important that when you look, if trying to make one hash rate estimate from looking at multiple samples, that you need to be looking at multiple samples of the hash rate, rather than coming up with a hash rate that's a mishmash of different difficulties and times that were taken against different difficulties. That's not like any kind of proof or anything, but
yeah. So I think that it's an interesting question. Like, should we be weighting the difficulty in and weighting different blocks by the difficulty that they had? And I think in practice, it's not a very big one, because the difficulty should be changing only by 1 or 2% over a typical 144 or whatever block interval. Like the time period over which we're doing this averaging should be fairly short with respect to the rate at which the difficulty changes. So
that's in healthy circumstances, though, right? I mean, I think situations where a chain splits, or where there's huge disruption about miners shifting back and forth, we do want to account for those as well, right?
Yeah. So I think it becomes more of a how do you respond to abnormal events kind of thing, rather than how do you statistically account for measurement error and statistical noise kind of thing. Because like the only times in which difficulty changes by more than a couple of percent are times when shenanigans are happening. And so trying to deal with shenanigans by using a statistics-based approach, where you're trying to maximize information density or whatever, that's just not the right approach. So
there's no downside to it, though. I mean, I think the reason, if you're going to run a test, and in Scott's test it worked out better. It's simpler to calculate, I guess, just counting the, but you have to show that there's some downside to it.
Yeah. So Scott, your test included like rapid increases or decreases in hash rate in attack simulation scenarios, right?
Yeah. The hash rate. Okay, if we reduce Bitcoin's difficulty algorithm down to 2 blocks, and mathematically you can't do it to 1 block, but if we reduce it to 2 blocks, the difficulty, the hash rate, and you average a bunch of those, and in order for it to come out to the correct average solve time, your difficulty your hash rate of each pair of blocks would be the sum sum of those two difficulties divided by the sum of those two solve times. So you got your number of hashes divided by time, so it's your hash rate, but you also got to divide by 2 because of the statistics. And you can't do it for one block because that factor is a divide by 0 error, or multiply by 0. It's multiply by 0. But it comes out perfect. WTEMA comes out perfect for if its averaging window is only 5 blocks or 2 blocks. It comes out perfect if it's 2 blocks if you throw in that divide by 2. If you do them in pairs instead of single. So the WTMA works perfect if you make that statistical adjustment. And so LWMA can go to lower times with having a larger error. So what I'm getting at is you can, by making the averaging window smaller and smaller, you can start seeing which algorithms are theoretically closer to the ideal. The bad ones start messing up as you get to smaller and smaller windows. And what I'm so excited about the assert is that you can make it very small, and it always comes out the exact correct solve time. And so that's why I suspect it's the perfect one. And I wonder, and I've been trying to use it to estimate from one block. What does it tell us the hash rate is if we have only one block? Because it's really hard to estimate it from one block. But for 2, I know how to do it. You add the previous 2 difficulties, divide by the previous 2 solve times, and then divide by 2 again, and that averages out over the long run. But 80 or 90% of the time, you're going to actually be underestimating the hash rate. The average comes out perfect over the long term, but a lot of times you're going to be underestimating because you're dividing by the 2. So those are the kind of things I'm thinking about.
All right. That was a lot. So there's obviously all these different ones. I was getting them all mixed up in the head. Is there like a clear front runner for the best one so far, or do they all have their own kind of trade-offs?
WTEMA, who would be against it?
WTEMA sounds good. So coming from there, say everybody agrees on the WTEMA. I guess how do we implement this, and how do we coordinate and basically get consensus to get this in November? I know the whole Bitcoin Cash ecosystem, I know there's been a bunch of internal politics, but I know everybody wants to improve the DAA, and I think that's the least controversial subject there is. So how do we coordinate and kind of do this?
Well, yeah. So hang on. I mean, I'm not sure we have I personally,
sure,
as far as what DAA I would vote for and so on, I don't feel I have a strong vote because I know work has gone on since I paid attention. Last time I looked, and I did take a close look back in the day, I thought the WTEMA it was close enough to what I think of as the theoretical pure EMA, which Jonathan was describing, where it's, literally just 2 factors, how long it's been and how many blocks there have been. It was close enough to that it would be it probably wouldn't have any serious vulnerabilities that would lead to oscillations, and it was very cleanly implemented, integer math, short code, easy to understand. So that was, at the time, I was a fan of that. But I can't say that I feel confident that of the different relatively similar EMA variants floating around, that's necessarily the one to go with. I would defer to the others here on that mostly.
Yeah, I kind of think that there are a lot of different good options. Like, I'd be perfectly happy with an LWMA, the linear version. I'd be perfectly happy with the assert. I'd be happy with the WTEMA. I'd probably be happy with Karol's algorithm too. It seems to be decent in terms of its performance, although I think that that might have been an accident. Like, I think that there's a lot of different things that work. And as long as you have no median of 3 filters, pre-filters, because those can be attacked and those can also contribute to oscillations. B, you have monotonically decreasing weights for blocks, as the linearly decreasing weights does and as the EMA does. And as long as you have some system for protecting against timestamp manipulation attacks, such as prohibiting any block that's more than 1 second in the past from the previous block or more than 30 minutes in the past or whatever, just some system in place. As long as you have all those things in place, I think that that algorithm is going to be fine. So yeah, I think that there are a bunch of, I think actually what we should probably be doing is instead of trying to pick the one best, ideal, most optimal, awesomest DAA ever, we should use approval voting. We should just say, hey, I'm okay with this option, this option, and this option, but not these 3 options. And once we find an algorithm that pretty much everybody's okay with and that more people like than the next best option, we just go with that. I think that there's a big potential here for bike shedding and for spending way too much time debating the details of all of the different options that are nearly equally good. And because we're spending so much time bike shedding, we fail to actually implement it. So yeah, I think that we kind of just need to write some code, and once we get a good option that is well implemented, well spec'd, and that everybody's okay with, we just go for it.
I agree with all that. The one thing I expect to be potentially bike shedded is this idea of selfish mining. This is something that came up in the previous debates about the direct algorithm, and the current algorithm has a special thing called finding the suitable blocks, where it takes the median of the endpoints and tries to, I guess, avoid a theoretical selfish mining attack. The thing about the selfish mining paper that it's important to understand is that the selfish mining paper assumes a perfect DAA, because it assumes that if you're able to reduce the overall hash rate, then your relative hash rate goes up immediately. So if you're worried about selfish mining with regard to designing a DAA and making it better, like, because that was what came up before, was if we're going to have a rolling DAA and not a 2,000 block window, this is going to make selfish mining worse. Well, maybe, but it can't be worse than the paper, because the paper already assumes that you have an infinitely responsive DAA.
Yeah, there was another paper a while ago, I think from, I can't remember who did it, but a paper on the selfish mining implications of actual real world DAAs. And they included Bitcoin Cash in there. And they said, that if you have oscillations in particular, or if you have some of the other real world problems in DAAs, the selfish mining potential increases dramatically. Like with the original et al. Selfish mining algorithm, you had the requirement that you had to wait 2016 blocks before you saw any benefits. But with real world selfish mining on multi-chain systems, you can just wait for the short 10 block burst in which the difficulty is below equilibrium, and you can do selfish mining right then and take more advantage of that short burst than everybody else. So yeah, the current DAA is really, really bad in terms of selfish mining. And what we want to do is to improve that as much as we can while keeping all of our other considerations in place. But yeah, there's also actually the selfish mining consideration that people are worried about with having a non-median based DAA is that a selfish miner might manipulate the timestamp of one block so that the successive block, the next block, either is easier to mine, thereby giving them an advantage, or more likely to be accepted as the chain by having a slightly higher difficulty. Like if you're choosing the chain that has the highest difficulty blindly, and if you have a block that has a 0.00001% higher difficulty than the competing block, then it would win in an orphan race. And that can be a problem that can be exploited by selfish miners. But there's a really easy fix to that. And it's just a matter of beefing up the first scene rule. So currently, like the first scene rule was written for the BTC context, the regular Bitcoin context, in which difficulty doesn't change except once every 2016 blocks. So you know that the difficulties are going to be exactly the same. With Bitcoin Cash, the difficulty adjusts every block, so that's not necessarily going to be the case. But you can patch around that very easily by saying that if you've got two chains, and this is the one you saw first, and you're considering whether to switch to this other chain, and the two chains differ by less than, say, 10% of one block's worth of difficulty, you don't switch. So you just need like a little bit of fudge room. You need a little bit of wiggle room around one block difficulty in order to prevent these selfish mining attacks.
Yeah, the selfish mining attacks, which let's say are those that someone with 33 to 50% of the total hash rate can gain an advantage, almost no advantage at 33%, and some advantage, more advantage at 40, 45%, and then it increases all the way up to 100% if you have 50% hash rate. Okay, now the attack, anything less than 50%, you can block that attack, almost all of them, if the rule is to don't switch tips unless unless the competing tip and your tip have 3 blocks. It'll take you about 3 blocks to be fairly sure that other tip does not have 50%. So that would block a lot of it.
I don't think that's actually necessarily going to work, because a lot of the selfish mining original proposal, the Amin bin Zayer and LIL proposal, depended on outpropagating your opponent. So if you're the selfish miner and you detect when somebody else announces the header of a block and the rest of the block is in full propagation, or it's waiting for the full propagation to happen, if you're really good with your block propagation, you can hear that header and then publish your full block before they get to publish their full block to some percentage of the network. And in that case, if you have this 3-block rule, that can actually work in favor of the selfish miner.
Okay. Yeah.
So yeah, there's actually that original method of selfish mining is just one of many different methods of selfish mining. And the difficulty adjustment algorithm doesn't really come into much play in that one. The concern is that a different difficulty adjustment algorithm might make new selfish mining attacks possible, specifically ones in which you manipulate the difficulty in order to gain a slight advantage in your selfish mining, such as by making a block that has slightly more work behind it so that you can always win the orphan races by just having your block be preferable. And yeah, I think that beefing up the first scene rule to have that fudge factor solves that pretty easily. And that can be done for any algorithm. It doesn't even have to be EMA.
Well, the outpropagation was part of it. That's the gamma thing. But if you assume that, yeah. So, but that was the difference in the original paper between the 25% and the 33%. It gave that much. But the selfish mining overall strategy was a multi-block thing where you can build up a big store of blocks and then just start chopping off the ones that are against you. And of course, the more hash rate you have, the easier it is to do that.
Yeah.
Anyway, yeah.
And even the
vulnerability, new vulnerabilities are always possible. It's just, my point is only that we shouldn't be afraid of making the DAA better because it's going to make selfish mining worse. Right,
because it's already extremely bad. And like, there's some really bad exploits out there that just aren't being used.
It already assumes that the DAA is better than it is.
Yeah.
right. I guess, do we have some more comments? Do we have any questions? I know chat was going off the rails a little bit, but
Yeah, I can't see the chat, so if you see any good questions in chat,
yeah, we'll do
leave
it.
them out.
They're just not
There aren't
marked up.
any.
Yeah, it's a gibberish at this point. So, like selfish giants are very dangerous miners, like stuff like that. So,
Oh, there was one other thing that I wanted to mention. So like I was showing the confirmation times. Let's see this one. So like we saw that big spike in January in confirmation times, and then it seemed to go back to normal afterwards. I want to mention that this problem is actually a lot worse than it looks. The reason that it went down is because in late January, early February, BTC.top or Jiangzhou personally decided to mine blocks at a loss whenever the current block interval started to exceed 1 hour. So if you look before, I can't remember the exact date, but like before January, BTC top was mining very few of the blocks in intervals that lasted longer than 1 hour. And then afterwards, they ended up mining something like 40% of them. So thank you, Jiangzhou. He's taking a big loss by doing this. And he's masking most of the severity of the issue by personally suppressing these extremely long block intervals. But we need to fix this issue. We need to fix the core issue because we should not be relying on the charity of big benevolent miners as a cryptocurrency.
great.
So
yeah, I guess if you had so with that model, could you maybe to wrap it up, kind of show some models of the proposed DAAs if you already have them on hand?
Sure. So like here's the simulation. This simulation does not have the assert proposal implemented, but it does have the current DAA or a very similar version without the median of 3. It also has the WT thing that, Tom, this was your original one, right? WT 144?
Right.
And then there's an integer-only EMA, and then a improved version called WT EMA or WTEMA or whatever. And it has a few different variants depending on the time constant or the scare quotes averaging interval.
Like the
and scare
responsiveness,
quotes.
yeah.
Yeah, the responsiveness basically. So what we see is in terms of difficulty, there are these oscillations in the current DAA in blue, and they're very large. Sometimes difficulty increases by about 50%, 60% over the course of a day. In actual BCH world, we've seen oscillations of about 20% per day. So this is a little bit worse than what we see in reality. But for all the other algorithms, the difficulty changes far less. And if you look, the orange one is the original Tom Harding one, the WT algorithm. And that one still has some variability, some fluctuations. It also has these weird downward spikes on occasion. But the EMAs do much better. You can also see that the 288 block time constant responds a little bit differently. It's actually time shifted. Like a certain block height happens at a different time. But overall, the longer constant has more consistent difficulty and also less rapid changes in difficulty in response to shifts in profitability. So like, I think that overall this shows pretty clear superiority of the EMA to anything else that's been proposed so far. with the possible exception of the LWMA, which isn't in this, and the harmonic weighted mean, which also isn't in this. So we've got profitability here. Different mining strategies in reality do have slightly different amounts of profitability. We want that difference in profitability to be as close to zero as possible. And the WTMA algorithms get close to zero. The WT algorithm gets kind of close to zero. And the constant weighted or the simple moving average DAA doesn't get very close to zero at all. It's a couple % usually advantage for being short-term greedy versus being a constant miner.
I believe the W weighted harmonic mean is going to be the same as LWMA. I changed the name.
Okay.
Kind of. It'll be great when you get one more checkbox on there for the simple EMA.
Yeah, the assert. So by the way, for the audience, assert stands for absolutely scheduled exponential retargeting, or something like that. I asked Mark if I could host this for him, and he agreed. So if you guys want to read this PDF, it's it's on my website.
Yeah.
toom.im/files/da-assert.pdf. Absolutely scheduled exponentially rising targets. And yeah, this is the formula right here.
And what's the site for the simulations?
The simulation. That's localhost. ml.toom.im:8051.
ml.toom.im 8051.
And that website has, so all the simulation code is server side, which means that there are some performance issues with having a bunch of people hit it at once. So the version that's online limits, I think, the simulation to 10,000 blocks, but you can also download the code from my GitHub. Let's see, difficulty.
I should mention, Mark seemed to think of this algorithm in about an hour. I followed the chat and people were asking him about them. And so he disappeared for a couple hours and he comes back with this. And then Tom Harding showed it to me. And I looked at it, it took me a while to think about it, and I tested it some, and I got really excited, told Mark, and he thought about it more, and out came that paper.
Yeah.
Later, the guys from Imperial College, I guess in London, come back and ask me, have you seen this algorithm before? We think it's great. I said, well, yeah, Mark just showed it a couple months ago. And so they've got their paper out now, and they actually do a proper, what looks like a proper derivation, and show that they did start with an exponential moving average idea and went through and then made a correction at the end and come up with the same equation. Or like I'm saying, Mark just puts it out there. He intuited it. He said, I think this would be good. And where they went the long route and figured it out mathematically, you might say. And then of course, Jacob was the first I know of that stumbled upon it. He did his own EMA kind of thinking and got close to it, and his work's good. And then he briefly tested exactly the same as the assert. And then to just put things in context, the WTMA I think was done by Tom, because he was trying to combine what Jacob had, and he wanted while using the WT 144, and I think that's how you came up with it, Tom.
Colin, I think one of the really things that's obvious for the future of BCH, looking at the graphs that John showed, and how even WT 144 still had imperfections in its response, was that if there was all this time pressure, like artificial time pressure, all these ideas we're looking at were come up with about 2 months after the DAA fork.
Yep.
Every single one of them. And if we had more of an approach of let's wait till we get the thing that works and that everyone loves, instead of we have to fork on November 15th, things would have been much better. So I think that's instructive because we're struggling with that. Or BCH is struggling with that future hard fork schedule right now.
Yeah, I think that's definitely an issue many are concerned about for sure. I would like to take this time to shill the site bitcoincashresearch.org. It's a forum dedicated towards more technical discussions. And so these types of discussions that we're having on here would be great on there. And so we're hoping to direct a lot of technical discussion there. So bitcoincashresearch.org. So.
Colin, I put a few links into our private chat. Can you copy those over to the group chat?
Yep, I forwarded them to YouTube.
Okay.
Yep.
I think I just have a couple more comments and then I'm kind of done, I think. One is just, to echo the Imperial College paper. I realize, they came up with this idea and other people had found the idea before, but the paper, I thought the paper was a really good read. In particular, like Jonathan, what you were talking about, it has a good discussion about the elegance of this, about how basically all you need to do to figure out the difficulty is to look at, they show how memoryless it is, because really all it is affected by is the amount of time that has passed since Genesis and the number of blocks that have been released. Like literally those are the only two factors driving the calculation, which is compared to like these averages we used to have where you sort of, take 200 blocks and divide them and all this. I mean, this is sort of so they talk about that elegance and explain it well, I thought. And just the second thing was a more speculative, just in case, people feel like they don't have enough nitpicking and hair splitting going on already. Well, one idea that I did have at some point that I never took any action on, and I suspect maybe other people have looked at, is just about the possibility of difficulty adjusting within a block. This is not something that should be on the table, I think, for any changes this year, but just as an idea to think about that might turn out to be beneficial if it turns out there are further oscillation problems or something. There is one problem we have right now is that the difficulty adjusts every time a block comes out. So the block is released and the block dictates what the new difficulty will be for the next block. But until a block comes out, the difficulty is what it used to be. So if you have a situation, and we have come close to situations like this once or twice in the history of these chains, if you have a situation where almost all, like 99+% of the hash rate disappears at once, and at that point you're stuck with a very high difficulty relative to the existing hash until a block is found. And that could just kill a chain, honestly. Like you can reach a state where there's not enough hash left, nobody finds a block, the difficulty remains high because the difficulty only adjusts when a block comes out, and so then your chain is just gone. So the idea would be, can you make the difficulty adjust such that if a day has passed with no blocks being found, a lower difficulty block will be accepted than would have been accepted a day ago. So I just leave this as something for other people to think about if they're bored, as you go to sleep at night to help yourself fall asleep, sort of thing.
I think it's worth mentioning that Bitcoin Cash is currently running into that problem on a daily basis. We are seeing usually about 90% of the hash rate leaving at certain times when the profitability falls below parity with Bitcoin Core. And we have a solution to that. It's not a solution that I like, but it is a solution. And the solution is Jiang Zhou'er and BTC.top. And like we're currently using that solution way too heavily. We should not be using that on a daily basis. But I think that for the scenario of rare anomalous events, that relying on a little bit of minor altruism, or I should say not altruism, but minor long-term self-interest is actually valid, because all SHA-256 miners want Bitcoin Cash to survive because it increases their revenue regardless of which SHA-256 coin they're mining. So I think that as long as we keep the average profitability loss for doing this kind of altruistic mining small, that we will see miners choose to mine a block if there hasn't been one for 2 hours at a loss.
I think that there is a sort of general principle, I think, of mechanism design here, of designing the incentives where, like in the worst case, we're counting on miners and other participants in the system to be long-term greedy, but the better we can make our system such that it's defended against short-term greedy participants, fantastic, right? Because when you're forced to say, well, they're not going to do this thing that'll make them a lot of money now because it would lose them money over the course of years. That's not ideal from a security point of view. Sometimes we may have to lean on that, and it's great that the miners are there to be leaned on in those situations. But of course, if we can improve the mechanism such that even the short-term greedy people get no profit from these exploits and so on, then all the better. So, but anyway, I'm not contradicting anything you're saying. Just to clarify one more time, then, just because it sounds like it could enter the sort of sphere of applicability here. The specific point I was making is that right now, when a block comes out, the difficulty that is required for the next block is 100% fixed until that next block is found. What I'm sketching is you could make it such that the difficulty of the next block depends not only on the difficulty of the last block, but also on how much time has passed since the last block. And this makes timestamp shenanigans and stuff much more dangerous, and there's a lot of problems, but it's just a possibility to think about.
I couldn't agree more, and you are a little behind on the research. I've put a link in the chat to the RTT paper, which is
yes. I thought. Sorry, Tom. I did want to say I thought you might have actually done some stuff on this. Go ahead.
He might have actually implemented it already and created a new coin that has exactly this property.
The problems Jonathan mentioned as far as my desire to reduce the future time limit to 10 seconds, 30 seconds, that would present a huge problem for the RTTs that's Tom and others are studying. It's as far as like being able to change during the block. You constantly, every, say, 30 seconds, you need a new template, and it needs to be a time that is after the previous block.
Yeah, well, to do it well as a miner, you would definitely have to make changes to the mining client side.
So, like Jonathan's saying, that would break a lot of equipment out there, which you could.
You could do it crappy though, without you making any changes, which is what's happening right now.
There is also another concern with RTTs, and the issue is that RTTs by RTTs I mean real-time targeting algorithms. Those are algorithms that adjust the difficulty of the current block candidate based on the current block candidate's timestamp, rather than not based on the previous block's timestamp. So with RTTs, there's one significant large risk, I think, for Bitcoin Cash that doesn't apply to most other blockchains. And that is that RTTs have the potential to increase orphan rates. RTTs will generally make the distribution of block intervals narrower. They will compress all the block intervals so that they are closer to 10 minutes. And that narrowing of the distribution results in a greater probability that two blocks are found at the same height at very similar timestamps or at very similar actual times.
That's true. You have to quantify it though. And also remember, as you mentioned, the flip side of it, as far as the advantages, or as Jacob mentioned, is stopping insta-mining, making it impossible, and also risk of chain freeze and chain death on the flip side of insta-mining.
Yeah.
So it just depends how big those problems are, how tiny your hash rate is.
Yeah, like I've mentioned that what you just said many times to Tom about his paper, like he's got his chain that's actually active and working, and it's very tight timestamps. But the ones I was promoting last year, you would have a baseline difficulty algorithm that was slow, a regular kind of slow one, and then you would have an RTT riding on top of it. So it would change maybe only 10% from solve times that are 0 out to 5 times your block time. Just the difficulty would start out high and come out slow, but the variation and all of it may not be, but only 10%. And this would stop a lot of that on-off mining because the hash rate here can jump 300% when the difficulty is changed only 10%. So in your chain work and your baseline your chain work would be based on your baseline difficulty, but not the RTT that's riding on top of it. And if it got a very long solve time, then it would prevent the problem that Jacob is describing.
Cool. So any last thoughts, and we'll wrap it up here. All right, sounds good. Thank you all for the discussion. I understood about a third of it, so hopefully we get a lot of technical people to watch us, and hopefully they can learn some stuff. So again, thank you all for being here. I really do appreciate it. So
Thanks, Colin.
Yeah, thanks for organizing. Great to see you guys.